What is theoretical mathematics about? What is its usefulness? Can a person not into mathematics understand what mathematicians are doing in theoretical mathematics? We are going to address such questions in today's video. Today's video is going to be about a key aspect of theoretical mathematics. With this, I welcome you to the Math Exploration Tour. So a key aspect of theoretical mathematics is to observe crucial properties of objects which we can see and try to define a new object with those properties. Well, what am I trying to say here? So this may not be clear at first place, but I'm going to illustrate that with examples. So the example I'm going to consider specifically is functions from R to R, the real numbers to the real numbers. What is it that we are going to talk about regarding functions from real numbers to real numbers? I believe most of you know about the definition of continuity for functions from reals to reals. The basic definition, which people learn in high school, is that we say that a function f from R to R is said to be continuous at some point C in R when the limit as x goes to C of f of x is actually equal to f of C. Well, this seems okay at first place, but one might ask, what exactly do you mean by a limit? What you are taught in high school is only that as x comes closer and closer to C, f of x also comes closer and closer to f of C. But still, this is not a very rigorous definition in the sense that it's a bit imprecise. We have not defined what it means to be closer and closer to. So there's this famous epsilon delta definition of limits, which I'm going to talk about very briefly. And if it's not clear to you, I'll be very brief in my explanation. If it's not clear to you, you can just search it up. There are various YouTube videos as well, which explain that well. So we are going to talk about the epsilon delta definition now. So what are we trying to say by saying limit x goes to C of f of x is equal to f of C? So suppose you have a point C over here. I'm going to draw another real line with f of C over here. One way to think about continuity is that you want to come closer and closer to f of C. That is something you need to verify. So suppose I say that I want f of x to be very close to f of C. So something like a very small neighborhood around f of c. I want f of x to be in a small neighborhood around f of c whenever x is in a small enough neighborhood of c. So let us make this even more precise. Suppose I'm given an epsilon neighborhood, which means that I'm given a neighborhood of length 2 epsilon, meaning from f of c, I go to f of c plus epsilon towards the right, and f of c minus epsilon towards the left. I go epsilon left, epsilon right. I want f of x to be within this interval whenever x is in a small enough neighborhood of c. This is exactly what we want to capture by saying that f is continuous. This is just reframing the limit concept. So how can we make this into a precise mathematical definition? So we say that f is continuous at c. F is continuous at c if for any neighborhood of f of c, which is characterized by this number epsilon, we'll say that for all epsilon greater than 0, for all epsilon greater than 0, we are referring to this neighborhood of length 2 epsilon around f of c. There exists a neighborhood around c. I'll call it to be, say, c minus delta to c plus delta, which means I'm going delta right and delta left. There exists, this is the symbol for all, and then this is the symbol for there exists in mathematics. There exists a number delta, which is also positive, such that whenever x lies in this interval, that is whenever x is between c minus delta and c plus delta, f of x must be between f of c minus epsilon and f of c plus epsilon. So trying to say this again, given a neighborhood around f of c, however small it may be, I must be able to produce a neighborhood around c such that whenever x is in that neighborhood, f of x is in the epsilon neighborhood of f of c. This is precisely what we want to say by saying f is continuous at c. Now we come to the major point. This was just a digression. Now we come to the major point. What is that property of the real numbers which helped us to define continuity in this way? Well, you would notice that the crucial fact is that you are able to measure the distance between any two real numbers. What do I mean by saying that x is in this neighborhood of c? X is in this delta neighborhood around c. I mean that x is between c minus delta and c plus delta. But another way of saying it is that the distance between x and c is lesser than delta. Similarly, when I say that I want f of x to be in the epsilon neighborhood of f of c, I just mean that the distance between f of x and f of c must be lesser than epsilon. So let me just write down that the crucial property which allowed us to define continuity is distance. So in this regard, we are going to make a new definition. We are going to define a new object altogether which has a distance, so that we can also define continuity for functions from that object to another object of the same type. What are these objects called where we can measure distance? These are abstract objects. For real numbers, you can see them. You can see them precisely, and you know the formula for the distance as well. Namely, the distance between any two real numbers, distance between any two real numbers is simply given by mod x minus y. But when we generalize, we can't really see what exactly is the distance function. It's just lying somewhere and it satisfies some obvious properties which we want. So in this regard, I make a new definition. What are these objects called where we can measure distance? The name for such objects is metric spaces. How do we define a metric space? We define a metric space as follows. A metric space is a pair x comma d, where x is an abstract set, just a set of elements, and d is a distance function What should the distance function do? It should take any 2 points in x and output the distance between them. So the distance function is actually a map from the Cartesian product x cross x to R, satisfying some basic properties which we obviously require. One, it's quite obvious that the distance between any two numbers is non-negative. When I say it's obvious for the real numbers. We are making an abstract definition, trying to make use of those properties. And further, we can obviously see in our real world that the distance between any 2 points is 0 if and only if they're the same point. So, and dxx is 0 if and only if dxy is 0, sorry for that, if and only if x is equal to y. And further, it's obvious that the distance between point 1 and point 2 is the same as distance between point 2 and point 1. Which means to say that dxy is equal to dyx for all x comma y in x. Third property. The third property which we want the distance function to satisfy is the triangle inequality, because it's an extremely useful inequality. What does the triangle inequality say? When you want to go from a point X to a point Z, it's quite obvious that you would rather go on a straight line rather than going to some other point Y and then going to Z. In words, it would just mean that distance between X and Z is smaller than or equal to the distance between X and Y plus the distance between Y and Z for all X, Y, Z in X. So this is the actual definition of an abstract metric space. We call it abstract because it's something which we can't really see like real numbers. In real numbers, we can see what exactly are the points, what exactly is the distance function, but here it's just lying somewhere. It's in some space. So now, why did we do all this? We can also define continuity between functions from a metric space to a metric space. How? Just let's recall how we define continuity for real numbers. We said that f is continuous at C if for all epsilon greater than 0, there exists delta greater than 0, such that whenever x is between c minus delta and c plus delta, remember that another way of saying it is that mod x minus c is lesser than delta. That implies that f of x is between f of c minus epsilon and f of c plus epsilon, which is the same as saying that the distance between f of x and f of c is lesser than epsilon. So now we are going to make use of this definition to define continuity over abstract metric spaces. So we say let x and y be two metric spaces, and f x to y is a function. It simply takes as an input an element of the set x and outputs an element of the set y. Is is a function. Remember that when I'm saying that x and y are metric spaces, it's a bit confusing in notation because I defined metric space, remember, to be a pair x comma d. But as in when we get acquainted with metric spaces, we do not really tell x comma d and y comma d prime be two metric spaces. We are just going to say x and y are two metric spaces. And let me just mention that this has a distance function d and this has a distance function d prime. Or a better notation would be this has a distance d sub x, this has a distance d sub y. So when can we say that f is continuous? F is continuous at c in x, obviously at c in the domain of the function, if the same definition for all epsilon greater than 0, there exists delta greater than 0, such that there we said whenever x is between c minus delta and c plus delta. But that doesn't make sense now because this is an abstract metric space. We don't have notions of subtraction and such things. In fact, we don't even necessarily have the notion of order to compare. But we know that that condition is equivalent to saying that the distance between x and c, or mod x minus c, is lesser than delta. So instead of saying mod x minus c, which doesn't make sense here, we're just going to use the distance function. That's that d sub x of x comma c is lesser than delta whenever this happens. Similarly, the distance between f of x and f of c, d sub y, because these lie in the codomain now. So f of x comma f of c is lesser than epsilon. So this is precisely what we mean by saying that a function between two metric spaces is continuous. Now, one may think that this is all, we can't generalize more. The crucial property was distance. We had to use distance. So we generalized it to metric spaces. We can't do better. But even that is not true. Let me just remark, I'm not going to go into the details over here, that there exist even further generalizations of metric spaces, which are called as topological spaces. Topological spaces are collections of certain special subsets known as open sets. And when you learn what is the meaning of an open set in real numbers or an open set in a metric space, you can actually formulate an equivalent definition of continuity just in terms of those open sets. This is the correct definition of continuity, but in fact, there is an equivalent definition of continuity in terms of some special subsets of metric spaces known as open sets. By equivalent, I mean that if we assume this definition, then under that definition also f is continuous. And if I assume that definition using open sets, if f is continuous using that definition, then it is also continuous using this definition, epsilon delta definition. That is the meaning of equivalent. But I won't get into the details in this video. It is for you to explore. So now that I addressed a specific example over here, it is an obvious question to ask. What is the usefulness of all this? One, the first usefulness we can see is that suppose we find suppose we find in the future suppose we find in the future a new mathematical object. And we find out that it has a distance function. It has a distance function with some formula, with some formula. Then much of our work is already cut out because we have already generalized it to metric spaces. Then we discover that this new mathematical object is also a metric space. We need not repeat all the work which we did for just the real numbers. So we have already done much work in metric spaces. We have defined continuity. There are several other properties of continuity, just like how we have for real numbers. There are various theorems regarding metric spaces. So much of our work is cut out in trying to analyze this new mathematical object. That is one usefulness. The second, the second use is in trying to understand basically which properties are leading us to correct theorems. So when we are trying to prove a theorem, when we are trying to prove theorems, we are trying to prove theorems. We realize what is the crucial point that is helping us to actually establish this result. What is the crucial property that is allowing this theorem to be true? For example, you will realize that this property f and g are continuous at some point x implies that f of x plus g of x, the function f plus g, is also continuous at x. You are trying to prove this. The result is the result is quite straightforward for functions from real numbers to real numbers. But what is it that is allowing us to establish that result? What is the crucial property of the real numbers which is allowing us to prove the result? If you do the same for abstract metric spaces, if you try to prove the theorem, you will realize that it is triangle inequality which helps us to establish that result. So let me complete the sentence. When we are trying to prove theorems, if we do so for, say, abstract metric spaces, for example, we will realize what is the crucial property. What is the crucial property? What is the crucial property? The crucial property of, in this case, R, or I should say objects that we can see in more generality, is the crucial property of R, which allows this theorem which allows this theorem to be true in nature. To be true in nature. So let me just recap what we did in this video essentially. So we said that the key aspect of theoretical mathematics is to observe crucial properties of the objects which we can see and try to define a new object, with these properties. And we gave an example considering functions from the real numbers to the real numbers. We introduced the epsilon delta definition of continuity, and we realized that what allowed us to define continuity for functions from reals to reals is distance. And we tried to define an abstract metric space in this regard. You can see the definition over here. Then we defined what precisely it means for a function from one metric space to another to be continuous. And then we described in detail what is the usefulness of all this. So this is essentially what is done in much of theoretical mathematics. This example is simply motivated from the topic of real analysis, which is just a name for theoretical understanding of calculus. There are various examples even in linear algebra where we try to define something known as a vector space, which is trying to generalize the concept of vectors which we can see in 2 dimensions and 3 dimensions to abstract vectors which we can't really see. You can even look up about vector spaces whenever required. So these material are things which are standard in any BSc or an MSc course in mathematics. So this is essentially what is done in theoretical mathematics. I hope this gave you a vision of what theoretical mathematicians do, and I hope you liked the video. So for more mathematics, please do subscribe to the channel. I'll be coming up with new videos with new ideas very soon. Thank you.